so let's get back to secondary structure. I talked about it briefly. Secondary structure, yes?
I have a pending question. What is specifically the profile?
What is a specific profile? Is that what you ask?
Yeah, what is the profile?
So what is a profile? Oh yeah, the exercises go about profiles at the moment. So again, when we align two proteins, the simplest way in which you can align them is you optimize the identity of letters. Then I showed you that there are some biophysical properties of amino acids, so you may not want to optimize the identity of letters. What you may want to optimize really is the biophysical fit. Biophysical fit means that a hydrophobic residue matches another hydrophobic residue. A charged residue, whether it's a K or R, is not important. Both are positively charged, so somehow they can be interexchanged. But you ought to really have K or R there. This is a biophysical feature, and such biophysical features are, for instance, measured in a generic exchange matrix, such as a Blossom matrix. Blossom matrix essentially measures how likely it is, without a structure, to change a particular amino acid into another amino acid. And it's much more likely if they have similar biophysical features, because then it will be a neutral exchange, right? That's a generic exchange matrix. And when you don't know anything about two proteins, you begin with this generic exchange matrix. Once you have these two aligned with this generic protein matrix, your problem suddenly becomes a different one. You now no longer, if your third protein comes into it, you want to align now a third sequence into it, you will no longer use only the Blossom matrix, but you will also look what are the places where things are conserved in the two that I already have aligned. Now, in the two that I already have aligned, I can look at a particular position and ask how often do I see a positive charge and how surprising is it to see a positive charge at the position. And this statement becomes the more informative, the more proteins I have already aligned. Because then, provided that all of the things that I have aligned really belong to the same family. If they don't belong to the same family, all of this is nonsense, you make a mistake. But if you build up a protein family, you add members of the family that in fact have all similar structure, for instance, then by correctly aligning them, you make a very specific landscape, so to speak. Landscape means you say at this position I have a valine that you cannot change. At another position you have a valine that you can change. And that is the specific profile. The specific profile no longer says, well, at that position you cannot change unless you also put a positive charge in it. The specific profile says, well, some positive charges you have to maintain, and others are seemingly not important. So the same amino acid V does not have the same probability of changing to any other residue at two different positions in a specific profile. In the generic profile, this is a 20 by 20 profile. Every V in the sequence will always have the same probability of being exchanged against any other amino acid. That's the generic one. That's what I take when I know nothing about two proteins that I compare. But the moment I've begun to build up a family, I know something about them, and that something is the specific profile. The profile, essentially, one way of thinking about it, the simplest way of thinking about it, you put a count of what you see, and you turn this count into a surprise level. Okay? Because count alone is not enough. So since the amino acids do not occur at the same probability, you also have to compute what's the probability of seeing that. So that's one thing. So more probable amino acids will have a different value there than less probable amino acids. And the other thing is that the probability of change also of course has to do with what is the overall identity. So if you have two proteins aligned and they have 100% or 99% sequence identity, that you see change is very unlikely. So if you have 30% sequence identity, you have 70% probability that there's change at any particular position. And this is another feature that you have to compute in order to compute is the variation that you see at any particular position, surprising or not. And that surprise level is the profile, the entry into the profile. So for every single position in the protein, say the protein has 99 residue, then the profile runs from 1 to 99. And its extension is for at every position, it has one of 20 possible amino acids, or values for 20 amino acids. Well, one is the native. But in fact, in an entire family, whatever protein you started with, the native may not be the most prevalent one. The one you happen to have started with may not be the one that has exactly the sequence that has the highest value, right? So it does not necessarily mean that that one is marked. Any other question? Or is that answered?
Yes.
Any other question? Yes?
Short question on that. How is the family defined?
So the definition of a family, many of these short questions are much shorter than the answer. And I'm sorry for that. Typically this is because there's not a simple definition. One way in which you can define a family is by saying everything that has a similar structure. That's the simplest way in defining a family. I showed you ways to put a threshold to decide when you can say that two proteins have a similar structure, and you have fairly, I mean, it makes mistakes the moment you get into the twilight zone, but in principle that is one way to think about it. And I believe in the context of this course, this is enough of a definition. Any other question? Thank you. So then we get into secondary structure. Again, words that you find in the Wikipedia, often something like secondary structure, and that leads to the statement 2D structure. 2D structure is very misleading because it's not two-dimensional. Two-dimensional is a contact map, is this thing here. Secondary structure really is writable in a string. There are 8 different states. When we look at the DSSP assignment that uses the hydrogen bond patterns, but they can be merged into 3 major states. So these are all helical states here, HGI. Typically the acronym that I will use is H for that. And there's the extended, the strand, and the beta bridge. So E and B is typically what I would call E. And then there are this TS and the space that I will refer to as loop or other. I showed you that some peptides are always in helix, some always in beta strand, some always in other, and here pentapeptides in both, because in fact they can be in different states because the contacts they have may be different. Maybe one protein, this pentapeptide, is in a helix. Maybe in another one there's another strand coming close to it, and that induces the formation of a strand. So it's long-range interactions that decide whether this pentapeptide then is in a strand or helix. Now, helix in a sense is local. What I mean by local is that if you take a window of 5 consecutive residues, you have the hydrogen bond formation in there. The hydrogen bond formation is between I and I plus 4. So in every window of 5, you see a hydrogen bond partner. While if you look at a beta strand or a beta sheet, the hydrogen bonds between 2 strands in the sheet are between 2 parts of the sequence that may be very far away. So this, in fact, the way the protein runs might be, yes, it's in the other direction. So the way the protein runs here is the first residue goes into this strand, then goes up here and goes into that strand. But it means that this strand and this strand, they are very far away in sequence. The simplest method to predict secondary structure would be take all the known structures, find the longest consecutive runs of some motifs that occur only in one of these 3 states, so that are always helical, that are always beta strand, and that are always other. That might be the simplest way. The problem is that you will find very few of these consecutive runs. So this is a simple method that you could do, but it will not bring you very far. The first actual prediction method that existed is much simpler than that. It comes from Shen-Gurji, and what he started with in his method had to do with the fact how proline looks. Proline is has an aromatic ring, and it, in fact, he assumes induces a change in the angle of the protein. And that, in fact, was the idea that this implies that the proline breaks a helix. Now, if a proline breaks a helix, then whenever you see a proline, you put the end of a helix and essentially you have a very simple prediction method. Now, this, in fact, was the first prediction method, and remarkably, this prediction method predates the first structure that we have seen. So this method was published in Science in '57, before we had ever seen a protein structure. Now, going from the odds of proline to odds for all, this is somehow an odds matrix, and we briefly discussed it. So here I have the 20 amino acids, and in this particular case, for simplicity, I have only 2 states. So I have the state E and other, and then essentially what I put into this matrix here is a count. So I take a large set of proteins for which I know the 3-dimensional structure, I turn them into secondary structure through DSSP, I look at some sequence unique subset, and briefly we discussed on last Thursday that this would give me around about 2 million or so cases, 2 million amino acids in one of these 3 states. And here what I show is simply the count. And the count in this particular protein, right? So in this particular protein, in total I have 1, 2, 3, 4, 5, 6, 7, 8 E's. So this is 6 and 8. So the E has a sum of 8, and the other here are the other residues, the blanks. So this would simply, this way you would build up a probability matrix. In this particular case, what I show you here is the part of the algorithm that does it for 1 protein. You repeat that for 10,000 proteins. And then you have simply a probability for a simple prediction method that simply looks up at a particular position. There's the residue R, and at residue R, at amino acid R, you simply look up what's the highest probability of the 1 in 3 secondary structure state of R. And that's the secondary structure you assign. That's the simplest method. And that is very similar to, in fact, a method that is known as 2 methods. One is Charles-Fassmann, the other one is Gore, from Barry Robson and Jean Garnier. And that is what I typically refer to as sort of the first generation method. Now, how do I get secondary structure in order to assess how well we do? And again, it comes from the PDB. You have seen PDB, you have seen how it grows. And in PDB, you convert the 3-dimensional structure by using this method, DSSP. When this DSSP was developed, that was in fact done in order to assess, to develop a secondary structure prediction method and to assess those methods here. Now, how would you measure the performance of secondary structure prediction? So here's what I show you is an observed secondary structure, and again the blank means there is the state other, and PRD is the predicted. So I have 2 strings, and my question to you, how good is the prediction? How do you measure the accuracy of the prediction? Can you throw a bunch of ideas at me?
The simple number of matches.
The simple number of matches. So you essentially would compute something such as what is often referred to as the Q3, the 3-state per residue accuracy, where you simply count for how many residues are correctly predicted in either of those 3 states. 3 states, that's why it's called Q3. And for this first generation method that I showed you, simple probability is 63%. No, actually, that was published. I'm sorry, 63% was published. When they measured with DSSP or later, then the performance looked more like 50%. Okay, 50% accuracy. So 50% of the residues are correctly predicted in either of those 3 states. Now, is that good or bad? It's the first generation methods, there are better things to come. What can you say about 50%? If somebody gives you a method, 50%, you don't have Google, you don't have internet, and you have to, for a change, think about what it means. So how can you think about it? Yeah? Just a second.
Random.
So compared to random. So what is random?
That would be like 33%.
So one way of saying random is 33%. It's not exactly 33% because they're not equally distributed. Since it is not equally distributed, the random number will go up, something like 35. So random is 35, you get 50. Do you wanted to say something? Or exactly that? Yeah?
was the last time that we had one of them already had 50% in the data bank. So if you would only assign one of them to all of it, you would also account to 50%.
So that I assume what you mean is, I'm not entirely sure. But you may have had this idea in the last lecture. So the majority state is the other state. And since the other state, in fact, is 50% of all the amino acids are in state other, 30% roughly in helix, 20% in strand, ballpark, roughly, right? If you have a method that always says other, that actually gets 50%. Is that what you meant?
Yes.
Yes. So you have a method that numerically on this Q3 score performs better than random, although, well, I'm not entirely sure how to call that method, but let's call it, at least it's not the most intelligent thing you can think about. It's an intelligent way to trick random. That I give you. Or it is, let's call it an intelligent random in some sense. By calling everything state other, you're not making a decision that that contains much more information than random in some sense, right? Let's not get into the detail of these words. It's not a clever method. Now, that brings me to another idea, or another question. So I showed you, and I will mostly, for the beginning of this lecture here, use this criterion Q3. But can you think about another score in which you could possibly assess how well secondary structure prediction does, such that this dumb method, the 50% that always says other, is not coming up high? What else could you look at? Yeah?
Weight of classes differently.
Yes, that's an interesting idea. So we can weight classes differently, but how would you come up with a weighting scheme? So by what you believe is right, but that's a problem, right? So you could weigh them. Well, how could you do it? Do you have any idea? So that's an interesting idea. So you could in fact, you could weigh according to the length of a particular segment. So long helices are more important than short helices, or than shorts. This is an interesting idea. And that brings up this issue of length. So you could take into account the degree to which you sort of match segments rather than individual residues. And that is a perfect idea, and we will get back to that later. There was another, I saw you, but only now. There was somebody else. No? Okay.
You could like do the weighting, but based on the observations that we had. So we just like counted each one of those and right away from those. So the calendar for one class was a...
I'm not sure that I understand what you're saying. So this is the problem. And I want to assess in a way that is different from Q3. And what do you say?
So what I'm saying is we could like count one class and then divide by the sum.
So we can count each class separately. So we could, in fact, rather than saying we have a Q3, so we count up all the residues correctly predicted in either of three states, we give three numbers. One is the fraction of correctly predicted helices, correctly predicted strands, and one is class other. That's what you mean? Yes. And those three numbers, then the question is so if you give them as three independent numbers, well, then you need three numbers. But then you would immediately see for this method that always says other, it would have 2 times 0. And that would stand out, right? You can possibly multiply them and take a cubic root or whatever. There are other ways of mathematical operations that you can do. But yes, so this would already be the simplest way that we could look at, although then we need three methods or some mathematical operation. Okay, that brings us to the next question. So this is I so far talked about the first generation method, and on Thursday somebody already had an idea how we can get into the second generation method. So the first generation method, again, it looks at the probability of an individual amino acid. It looks at the log odds table that I showed you. How can you improve upon that knowing that what you want is somehow interactions not only from that central residue, from one residue. You know what is important for secondary structure formation is how this residue is bound to other residues. So somehow, in computing your prediction score, you want to integrate knowledge about this residue binding others. How could you do that? Any idea? Yeah?
You could look at a window of multiple proteins.
So instead of looking at a particular amino acid, you could look at, say, 5 consecutive amino acids. And in Thursday, the first method that was suggested was in fact a K-mirror method, where K, in this particular case here, for my hand, would be 5. We discussed on Thursday that for a K-mirror approach, using 5 is impossible. We have about 2 million examples. 20 by 20 by 20 by the power of 5 is 1.6 million, which means we have about the same number of free parameters for a K-mirror as samples. And that is not enough. We need several, in order to do a K-mirror method, we need several samples for each possibility. But we could still build up somehow a window of consecutive 5 and look at the probability of a window. And that's precisely the idea of what the Gore-3 method is doing. Again, from Barry Robson, the math comes from Barry Robson, the biology comes from Jean Garnier. And the idea really is you take a window, shown here is a window of 7 consecutive residues. And for these 7 consecutive residues, you essentially have one residue at the center of this window here, and you predict the secondary structure for that particular residue at the center. These 3 on that side and these 3 on that side, they are the condition, define a conditional probability. So you compute the conditional probability depending on what is here in relation to what is next, what is flanking. And this is not the 1.6 million problem, because now you get flanking probabilities for every C. So you move this window through a protein of 100 residues will have 100 windows. So if I have 2 million residues in the database for which I know secondary structure, this will have these 2 million examples, and I will have 2 million of these windows. Okay? So I simply have counts for each of these positions, for each of these 7 positions. And that's very simple. So we have a window of 7, and for each of these 7, you sample 2 million counts. Yes?
Is it beneficial, or does it change if, does anything change if you have W different for I and J? If you have the number, W is 3 over here, and we're adding and subtracting 3 both ways.
No, so this is just the math for saying, well, it depends on how you do the math, right? You can say my 0 I, and then the leftmost is I, and then I do I plus 7. Yeah. Or I can do minus plus minus. This is all, the math is just done here. The counting of the index is just symmetric. That's all why it's minus. This is just the way of writing it. When you have a position I, you can do with respect to that position. Now this is important, however, in a different context. Since we are on it, let's just do it. I have a protein from residue 1, 2, 3, 4, 5, 6, and let's just assume instead of 7, I only have 3. So in my first window here, I would take those 3. In my second, I would take those 3. Now, the way the method works here is that I always predict the secondary structure of the central position, right? And then I move the window. Who sees the problem?
On the sides?
I'm not entirely sure what you mean by on the sides.
Like, if I want to get the number 6 to be the center of the window, then I have unbalanced windows somehow?
There will have been some unbalanced. I'm not entirely sure what you mean by unbalanced windows. So I move over here, and at some point 6 will be in a window. Is that what you mean, or?
So we are predicting the one in the middle, right?
Yeah.
So if we're at 6, then we have, and 6 is the end of the sequence, then we have 3 missing residues.
Well, in this particular case, we would, in fact, this is the same thing. Yes, we would predict the secondary structure for position 5. I'm not entirely sure whether you're seeing the problem or not, but yes, you are sort of seeing it. So actually this is, I find it difficult to, typically I repeat the question, but in this particular case, I find it difficult to repeat the question. For the examination, you have to really nail it. When we are here and you ask questions, I can interpret your question and I can guess, and then the guess can be right or wrong. And there's a communication. For the examination, there's no communication going on. So you have to really nail it. In a case such as this, I would have to mark it as I don't get it. So the major point, does somebody see the major point? Yes?
I think that one that you said, when you have like you want to complete the 6, and it will be the 6 the center, you don't have enough information in the window.
Yes. So I'm totally happy, that's exactly the point, but this is what I meant. You have to nail it, and you didn't nail it well enough. I don't know. So the problem is in the way I show it here is for 1 and 6. It's not only at number 6, right? The problem is already coming here. This way, I cannot predict secondary structure for position 1. And if my window is 7, in fact, I skip the first 3. So if I take the window as it is shown on the whiteboard here, then the first window that I can actually predict for is 4. Because there are 3 left, so the 3 minus, or the mathematical count here. But there are 3 amino acids before the first in the window of 7, right? Here it's in the window of 3, there's only 1. So how could I solve that problem? Well, I can just simply say this is not a problem because most proteins are 100 residues long. So if I have a window of 7, I throw away 3 at that end and 3 at that end, so I lose 6 residues. Okay, but if you want to make a longer window, you're beginning to see that certainly for shorter proteins, you're going to throw a lot away. So how could you address that?
We may add some padding characters.
Exactly. Great idea. So I add a 0 character, I add a 0 count, I add a null count, or whatever you call that. So I create amino acid 21. And amino acid 21 is completely in silico, completely artificial, standing for before or after the protein. I could have 22 for after, and 21 before and 22 after. Turns out that doesn't make a difference. So there's one new pseudo amino acid that counts for anything before the protein and anything after the protein. It's the simplest solution, and in that particular solution, you really can have the first residue in the center of any window and fill it up with this 21st. Now, any other questions so far? Yes? Why does it always have to be the center? Well, you could so one way of doing that is you could simply say, I'm going to predict, I'm going to compute. All that is relevant is here how you compute all the numbers, right? And if you compute the numbers consistently, you could also say my first amino acid is the one that I predict for. For this problem that I talked about the 0 value, it doesn't matter because then the problem will be in the end, right? So you don't get away from creating the 21st amino acid. In principle, this is symmetric. Now, the idea why it's put into the central is because you want to know, so you don't quite know in which direction the amino acid or residue I binds, in that direction or that direction. The helix could be in that direction, it could be in that direction. And you want to have a sensor that is somehow symmetric in a similar distance. But people have tried, so this is a sort of motivation, but in fact, I have no other answer to your question as in I tried this, it didn't work as well. Ultimately, at the end of the day, is as simple as that. And once you find this result, you begin to understand or explain that is because essentially the situation is symmetric, and you want to have somehow, but I don't know whether it's true. It just works worse. Any other question? Okay, so there are problems with this method that we have so far. Problem number 1, well, it's less than 100% accurate. at some point people argued that the highest you can achieve is 65%. What do you believe they claimed 65%? Well, let's get to that in a moment. Let's first get to the argument. Why 65%? The argument was it is local, meaning helix formation are local, and that is what I somehow see in these windows, but strand formation is not. Some of the other formation is not, and not all of the helix formation is always visible in a local window. So this information you don't have. This is why pentapeptides can be in two different proteins in different configurations, and you're not having all of that information. And the 35% of the secondary structure is determined by long-range interactions. How do you believe that people got to the number 35? Or the other way around, maximum is 65%, Q3. Where do you believe this number came from? Yes?
You said the random was 45.
I'm sorry. Yes?
You said the random was 35.
Yeah, no. So the point is that I looked at him, you believed I looked at you, so we start talking.
So you said that random was 35, so maybe that's a compliment.
Oh, that's an interesting idea. So the idea here is random is 35. The max I can. I love that. The max I can get is 65. Now the question is, what does random have to do with this number here? Anybody? I'm sorry, I put you on the spot, and that is totally unfair. I bet you, if we voted who likes that as an idea, we would get many counts on that idea. Most people don't say anything anyway. But what I most likely will get, and it's too late to really do this, most likely what I would get is 4 people or 5 people believe this is a good idea, 6 people believe it's not, and everybody else doesn't say anything. Which means there's a lot of support for your idea. It's still wrong, it has nothing, so the random number is... So this idea is that there is some formation that is non-local that determines secondary structure. That has nothing to do with randomly throwing a coin. Randomly throwing a coin is simply the probability of having secondary structure 1 in 3, a dice. And these two things are not related. Funny enough, those are similar numbers, and that is a very interesting point. We do that very often in science, where we see similar numbers and we jump on it and we associate them. This is the strength of human association, the strength of scientific investigation, and it's also the danger.
Could it be because beta strands and helices share characteristics in the residues of phenomena? So earlier you showed the Venn diagram.
Ah, that's a great idea. So maybe from looking at what is unique, what are unique peptides for helices, what are unique peptides for beta strands, and then looking at what fraction is shared, and maybe from that you somehow can gauge what is non-local. That's a great idea, but people didn't do that. That possibly could get us in a direction of sort of gauging this. It's a clever idea. I would have to think it through a little bit more. Yes? So I do not know, and again, sort of voting for a proposal, I'm not sure. So let's put this proposal up. So he says, so this time, for your proposal, I immediately gave a feedback, and then there's no way to vote. So the statement is, so they put up a method. That method says we can do 65, or a couple of methods. They never got better than 65. So that's why they said 65. Who believes this is the explanation? 1, 2, 3. Oh, you have to go, come on, you have to vote for your own idea. Oh, this is weak. So 2 supporters. Who believes it's not the right idea? So in this particular case, we have absolute majority, and this is a large majority who's against. It's not always the majority that works. So this is absolutely correct. People tried for many years, for almost a decade, to develop all kinds of ideas, methods, and then came machine learning, and machine learning also hit its head against 65. And I'll get back to that in a moment. So then they argued, if no method gets ever higher, this is the limit for what is local. Okay, we can get back to that. There's another problem, that in fact most of those methods predict beta strands at a level of less than 40%. So in the simplest model where random is 33, so 1 in 3, so 40 is less than 40 is close to 33. This is very, very close to random, and the argument again was this is completely understandable because beta strand formation is just not local. There's a third problem that I refer to as short segments. What I mean is, in a typical prediction, you would, this is the observation here, up in black the sequence, and the typical prediction would be down here. Now, for a typical prediction, you know that a helix has to have at least 4 residues, so this is 3. Does it mean that the helix actually here is longer? This is 5. Is that a longer helix, or should you just switch the helix and turn all of that into E, or is it all other? The same thing here. So if you have these short bits predicted, you don't know whether they are spurious signals that you should convert into other, or whether you should sort of interconvert them, so you don't know how to use it. That's the problem with short segments. And that brings us in an insert to a machine learning device. Historically, one of the first that has been applied for secondary structure prediction has been a neural network. So the basic idea of a neural network is you have units that are connected. Here, the J's. The units have values, here 1 and 1. And in order to see what comes into the green unit here, you multiply the value of that unit here, 1, times this value of this connection. That is what comes into the green one. Then there's a switch function. The switch function introduces a nonlinear element. So the first situation here is essentially vector multiplication. Okay, you have the vector spanned by the input multiplied by the vector spanned by the connections, and this is a simple vector operation, all right? Now, in the switch function here, the nonlinear switch function, and is shown here the hyperbolic tangents, there are other sigmoid, so sigmoid function is typically used, but they look alike. So ultimately very high, if what comes in here has a highly negative value, it's switched to 0. If it has a highly positive value, it's switched to 1, and then something in between. And this something in between, you could also put some other function into it. Hyperbolic tangents is just one that is very easy to differentiate. Okay, so this is the nonlinearity, and the kind of thing that you can do with it is you can classify points. For instance, here, sorry for the quality, so we have 2 types of points, the black one here and the white one, the open circle. So you want to classify in a different way. The way you train this device here, at any given random initialization of these connections here, you get an error. So by the function that I showed you, you simply multiply the connections that you have, random initialization times the input that you have, you put the trigger function, you get an error. That's the output of the network here. Then there's an output that you want. So say the black one here you want to put on an output of 1, and the open one here on an output of 0. So then you simply see what you, for every single of these vector, here you want a 1, here you want a 0. So this for the black one this is 1, for the open one this is 0. And you square because you make it sign independent. That's the error that you have in this network. And the way you optimize the weights, or you train the network, is you have some landscape of this error that I showed you with respect to the connections. And you simply go downhill with some possibility to move uphill. Okay, so for the 2 patterns, ultimately 1 goes to 0 and 1 goes to 1. And the way you train that is, let's begin in the first step here. Say these are the initial, well, it's not really randomly initialized. So in my universe here, I chose connections that are all 1. It's not a randomly likely situation, but simple to show. My first vector is 1 and 0, the second one is 0 and 1. So this one here, 1 times 1 is 1, 0 times 1, so this is 0. this will also get to 0. Now, in order to make these two, they have the same output, okay? So in order to make them differ, we will have to increase this value here and decrease that value. Okay? This way, this input vector, this input sample 1 here and these input sample 2 here will tend to give a different answer. The first iteration here still doesn't do it. For the second iteration now we begin to see a slightly differential answer, and then you keep going, okay? What this thing can do, it can introduce a line to classify points. And what I show here is these open circles and the dark circle, and there are 4 different lines that are equal in the sense they all train to 100% accuracy. So they all solve the problem completely correctly. How can you separate these points on the right hand side here with a line? So some people believe there is no line. Think again. It's a trick, of course. Yeah.
You could map the point into a different space.
That's a complex answer. Yes, you could. Well, simpler. Yeah, I said you cannot do it in a line, sure. I suggested to you that's a straight line, and of course this is mathematically what it does, the system. It introduces a straight line. And by a straight line we cannot do this problem. If we could introduce a line like this, then we could. But in fact, mathematically, the only way to do that is in this way here, that we introduce 2 lines. And 2 lines in the network idea is you introduce a hidden layer. And this hidden layer now, you can also think about it, in particular for a support vector machine that has a similar math underneath. You can think about it as you transfer the problem into a different dimension in which the separation now becomes linear again. And that was the idea that you had. So in terms of the math, this additional layer here is the same math. You still multiply the connection times what comes out here, that gets in, you do the trigger function here, you multiply what comes out, this one here comes out from here, multiply with the trigger, with the connection here, and that gets in there, and you have another trigger function. So you repeat the same thing. Just the same mathematical operation, okay? Nothing different. And also in the way you train this, really is nothing different. You train by going down in the landscape of error that you have here. And you do that by going down such that you reduce the error. At every single time step, t+1, you change the connections in a way in which they are negatively proportional to what you have with the derivative to the connection. Very simple. You go downhill is what this term means here. This could get you trapped in a local minimum. For that reason, you allow uphill moves. This is the so-called gradient term, or momentum term that you add. There are different words for that. So this essentially goes back into how much did you jump in the time step before, and allows you to go a little bit uphill. That's the entire training operation of a neural network. Very simple. Essentially, the problem really is CPU time. So you have to do that many times. But in principle, this is a very simple thing. Now, the idea is that you sometimes will overtrain with these devices, not the idea. You will very early see that you overtrain. And overtraining is illustrated here, where you show training time and you show performance. Can somebody tell me what green and blue means? I haven't said that. Does anybody know anyway? Yes?
Green can be the training accuracy and blue the test accuracy.
So green is the training accuracy and blue is the test accuracy, and this is essentially why we call this point overtraining, because at this point you see that testing no longer improves. In fact, it decreases. Why does it decrease? So let me first explain to you what testing means. I take my data set, and we get into this idea of cross-validation, and we will spend some time on this idea of cross-validation. So this is the set, symbolizes the set of all my known samples. In the simplest version of it, I take 1/2 and take it for training, and 1/2 and take it for testing. So the half that I take out will simulate the data, or with that half I try to simulate how the data will look that I don't see today, that I will present to the system tomorrow. Unknown data. That's what I simulate in the test set. So half, it could be a different number, but half is taken out, optimized on the green, and blue goes down, green goes up over training. Why? Yeah?
Because you might overfit your data while training. So,
what does it mean to overfit?
I mean, to have one line which classifies all the training data 100%, and but that will not be probably classifying the test data 100%.
So ultimately, now we get into the major assumption here. The major assumption is that the machine learning device extracts some common or generic principle of the problem. Overtraining means we have reached the point where in fact it does not extract any generic concept anymore. It learns by heart what is valid only for the training set. So this is no longer generic, this is no longer general. And that is why training set improves, test set decreases. Because what you add after this time here is simply specific to the training set. It's simply something that is not relevant for a data set that you will present tomorrow.